You see this right here? This is an IP camera. It's your typical IoT device. In this video, we are going to extract the firmware from this device, and we're going to reverse engineer it. So we're going to get started with the video. So to speed things up a little bit, I did remove the actual board from the outer housing of the IoT camera. When you get the camera out of the housing and you disconnect everything from it, this is what it looks like. There is also this piece right here that I went ahead and removed because this is not needed. So we'll put that to the side. And this is basically what we have right here. Standard IP camera, typical IoT device. This is what the back side looks like, and this is the side that we will be focusing on in the video. And if we can get a little bit closer here, you can actually even read the name off of the main chip here. So here is the CPU. Here's the main chip on the board. This is where the micro SD card goes. Here's a reset button. And the chip that we are going to be attaching the SPI flash memory programmer to is going to be this chip right here. It actually has a green mark on it. And typically you know which chip is the SPI flash memory chip. In this example, we have what appears to be two identical chips on the same board. They both have 4 legs on each side. They are both the same size. So how would you know which one is which? Well, you could just try each one and just use trial and error. But typically, the one that is closest to the CPU is going to be the SPI flash memory chip. And in this example here, they've further made it identifiable for us by putting the green line on it. So this is the one that we are looking at, and you can actually see that there is a little dimple on the corner of that chip. We want to make sure that the red line on the ribbon cable is going to the leg that is marked by this dimple. Okay, so let's briefly talk about the tools that we are going to be using. And inside of this tool bag, I have my go-to hardware tools for reverse engineering and hardware hacking. Of course, we have to have the multimeter, which I primarily use for determining the ground pin by doing a continuity test. And then over on the right-hand side, we have a handful of different tools. Up here at the top, I have a Raspberry Pi debug probe that is designed to work with the Raspberry Pi. I have my logic analyzer. I have my USB to TTL adapter. And finally, we have our CH341 programmer, also referred to as an EEPROM BIOS programmer. And this is what we are going to be using for this video. So here is the BIOS EEPROM programmer without anything else attached to it. And then here is the chip clip that is attached to the ribbon cable. This is what I call it, is a ribbon cable. There might be a different name for it. Feel free to correct me in the comments. And then at the end, you have one of several adapters. Once again, that's what I'm calling it. There might be a more appropriate name, and if so, feel free to correct me in the comments. So what we want to do is we basically need to attach the adapter and the ribbon cable to the BIOS EEPROM programmer. And you see that there is this lever right here. We push that up to basically open this up. That will allow us to insert the adapter inside of it. Now what I've done is I went and made this easy for myself, and I've actually marked both the side of this and this so I never forget which way that this goes in, because in the past I have confused myself as to which way it needs to go. So I'm just going to align the marks that I have previously made, and this is what it looks like connecting it. Let's just put it in like that. You can see from the side that's what it looks like. And then to secure it in place, I pull that lever back and that locks it. Now I can't pull that back out, and it is locked in and we are good to go. This is probably the trickiest part of this whole process. It's going to be a little finicky. You have to make sure all of the contacts on this chip clip here are connected and touching the legs on the side of the SPI flash memory chip. And once again, there is that dimple in the corner of the chip, and you want to make sure this red line on this cable, which is running to a specific contact inside of these plastic jaws on the end of the chip clip, you want to make sure that that red one is the one that goes over the leg where that dimple is. Okay, I feel pretty confident about that. Let me go ahead and give you a close-up of what that looks like. There's a side view of the chip clip connected to the flash chip. You just want to make sure that all of those contacts are in fact touching the legs of the flash memory chip. Okay, so we have the chip clip properly attached to the SPI flash memory chip on the board of the camera, and you can see the cable is running into the EEPROM programmer. We have that connected properly. The EEPROM programmer is connected to a USB cable. This is something that just makes things a lot easier so that you have more room to handle the device, and you don't have the EEPROM programmer plugged directly into the side of your computer, whether it is a laptop or a tower. It just makes things much easier. So the USB cable extender is running from the EEPROM programmer around my desk, and ultimately it's coming back over here into the side of my laptop. And on our laptop we are using Kali Linux. So let's go ahead and go down to the command line, and we are going to extract the firmware. First thing that I'm going to do is I'm going to create a directory to store the firmware and any other things that I'm doing. I will call that directory Mercury, because that is the name of this camera. CD inside of the Mercury directory, and we are going to use the flash ROM utility. If you do not have it installed, it's very easy to install on a Debian based system. Just run the command sudo apt install flash ROM. We can pull up the help menu for flash ROM by running flash ROM -- help. The main thing that you are going to need to know is what kind of programmer that you are using, because there are several. The one that I am using in this video is a CH341A_SPI, and you can see that that is in this list. Once you've identified the programmer that you are using, you can go ahead and execute the first command. We are going to run the command flash ROM with a -P for programmer, and we are going to specify the name of the programmer, which is CH341A_SPI, and hit enter. The main thing that we are looking to get from this is that it does correctly identify the flash chip. You can see that it has found a Giga device flash chip, and here is the name of the chip. Now in the past I have had some issues when trying to run the flash ROM command and specifying the name of this chip because of the brackets that letter B falls inside of. So I'm going to make an attempt here, and we might have to do some trial and error on this. So I'll do -C for chip. I'm going to give it the name of that chip, and I am going to put the brackets in there, but I'm going to close everything in single quotes and see if that will allow us to run the command. And finally, I will do a -R for read, and we are going to have to give the file a name because it's going to not only read the contents of the flash memory chip, but it's going to save the contents to a file. So we will call that file mercury.bin, and I will hit enter. And it is reading the flash. So one of the key takeaways from this is that you have to get the syntax right, obviously, but putting the name of the chip in single quotation marks allowed me to get around any previous syntax errors that I had come across. So we're just waiting for it to finish reading the flash. It should be momentarily. Alright, and it has finished. So let me clear the screen. We'll do an ls, and we now have a firmware image called mercury.bin. Let's go ahead and run ls-lh to get the size and human readable format of this firmware image. And it is 8 megabytes in size. Alright, so this is wonderful. We have now extracted the firmware from this IoT device, this IP camera. Now what? So now that I have the firmware image on my machine, I am actually going to transfer machines, and we are going to pick back up in this video after I have transferred the firmware image over to my main machine here. So at this point, you might be saying to yourself, well, you know, that's great, Mr. Fresh, or whatever the hell you call yourself. You can extract the contents of the SPI flash memory chip, you have the firmware, etc. and so forth. But I want to follow along with what you're doing, and I don't have the firmware. Well, you can get the firmware. So I have a GitHub repository. I haven't been very active on it, but I'm going to become more active on it. Over here at github.com/Douglas Fresh Habian, I have 4 repositories currently as of the recording of this video. One of those repositories is called mercamfirm. If we click on that repository, we are brought to this page right here. And this contains the firmware that I dumped from the Mercury IP camera. The same firmware that I just dumped in this video. So all you have to do is do a git clone of this repository, and you have the same firmware that I am using in this video, and you can follow along and do everything that I am doing. So we come up here to the green box that says code. I'll click on that, and we are going to copy the HTTPS URL. I will go down to the command line inside of my terminal emulator. We will simply type in git clone and paste in that URL. This URL will also be in the description for the video. Once you have finished cloning the repository, you can cd into mercamfirm, and if we do an ls, we have a hashes.txt file. We have a README file. We have a user manual for the camera. And we also have a directory called Mercury. If I do an ls on that directory, this basically is storing some photos of the camera and the board. So for example, if I were to use the open command and I will just pick one of these JPEGs, don't remember which one is which, but we'll open one up and see what we have here. Let's take a look at the hashes.txt file. So inside of this file we have 4 different hashes. We have an MD5 hash, a SHA-1 hash, a SHA-256 hash, and a SHA-512 hash. Basically what these are used for are to verify the authenticity and integrity of your firmware. What do I mean by that? Well, I will give you a more concrete example. Our firmware is called mercury.bin. This is what I've saved it as. If I were to use one of those 4 hashing algorithms, we will pick the MD5 hashing algorithm. I can run the command MD5 sum on that firmware image, and we get back an MD5 hash. This is the hash. I can then compare that to the MD5 hash that is stored in the hashes.txt file. And you can see that both of those hashes match. And we can do the same thing with the SHA-1, the SHA-256, and the SHA-512. That's just letting you know that you have the correct firmware image, that nothing has happened in transit, that nobody has modified it. Can open up the user manual, and this shows you what the camera looked like before we pulled the board out of the case that it was in. Gives you a description of it, the specs, the features, etc. and so forth. And the app that goes along with this is the Tuya Smart app. So it's just 2 pages. The main thing that we are looking at here is we have the firmware image that I have called mercury.bin. So we can do an ls-lh on that firmware image. We get the human readable size of approximately 8 megabytes in size. Before I unpack this with binwalk, there are a couple things that I like to do. One of those things is I like to run the strings command on the firmware image. With this one command and this one command alone, you can get so much information from a firmware image like this one, as well as many other ones. If I were to just run strings by itself on the image, we'll get back quite a bit of information, but this is not good because you can see a lot of the output. They're very small strings that don't really make much sense to us. So one of the things that I like to do is I run the strings command and I do a -n and I specify a number. The number I typically like to use is 10. And what this means is that it will only print human readable strings from the firmware image that are at least 10 characters or more. So now if I run that on the mercury.bin file, what we get back is an output that contains information that is more useful to us. We still have some strings, such as in this section right here, that seem to just be meaningless to us, but the majority of the stuff that we now have in our output is stuff that makes sense and is human readable. So we have boot arguments right here, we have what appears to be numerous function names, etc. and so forth. It might be beneficial to save all of the strings to a file. So I might, for example, rerun that command and redirect the output into a file called strings.txt. Now I can do a word count on that file and we'll see that it is 2,183 lines long. We can open that up and look at it. And from this point we could use grep, and we could grep this file for particular strings of interest. So I might cat out the contents of this file and pipe the output into grep. We'll do a -I for case insensitivity, and we'll look for any string that has to do with SSID, as SSID would be the name of the network that this camera connected to. And as you can see, we get back a lot of information. And in red, we have the string SSID, and you can see that right here we have an SSID. So this would be the name of the Wi-Fi network that this camera was connected to. There's so much information here. It is unbelievable, and it's unbelievable that you can get all of this information simply from a firmware image and using strings. Not even unpacking it, not going any further. We have the last date that this was updated. Right here we have a production server endpoint. Here is the vendor of the camera, which is Genie. Here is the device ID. Here is the camera model number. Here is the version of the firmware. Here is what appears to be some form of an account number. Absolutely incredible. We could also use grep directly on the firmware image. So I will do grep with a -A, an I, and a B. The -A will tell grep to treat the firmware image as a text file. The -I will use case insensitivity, so that means that whatever string we grep for, it can be in upper or lower case, and it will find the string. And the -B is to give us back the byte offset for where the string is located. So we will look for any strings that contain the word root. And we are running the grep command on the firmware image that is called mercury.bin. So if we take a look at the output, you can see that we get back several hits. In green, we have the byte offset. Here is the first example of our string of interest, which is root, and there are several instances after this. Each time you see the green, this is the byte offset for that location for that particular string. And I will give you one more example. So we can run the same command, grep with a -A, I, and B, and this time we will grep for the string pass. And this obviously could show up for many reasons, one of those being anything that has to do with passwords. And we'll hit enter, and once again we get back several hits, and the first thing that I see pertains to password information. Once again, over here on the left in green, we have the byte offset where the string is located, and we have several hits that come back. Okay, so we are still inside of the Merc Cam firm repository that we acquired from my GitHub page, and we're going to continue to work from this directory as our parent directory for everything that we continue to do in this video. We're going to use a tool called binwalk. To install binwalk, it's very simple. Run the command sudo apt install binwalk. You can pull up the help menu by running the command binwalk --help. There's a lot of options. We are only going to be using one or two of these options. The main one is going to be the lowercase -e option, and the long form of that is --extract, and that will automatically extract known file types. Another one that we might use is the -M option. The long form is a word that I'm going to pronounce as matryoshka. No idea how to pronounce that really, but it is used to recursively scan extracted files. And that is it. We can actually run binwalk on the firmware image without any options, and that will not extract anything, but it will simply read through the firmware image and it will print to the screen everything that it finds using those magic signatures. So I'll run binwalk on the firmware image, we have 3 columns. One of them is the decimal, another one is the hexadecimal, and then we have the description. So we have some XZ compressed data. We have a header for what appears to be the kernel image. But the thing that is of interest to me is the Squash FS file system. Squash FS is a compressed file system that is commonly found in embedded systems. So inside of this Squash FS file system is where we are going to find the root file system for this device, and that's going to have the bulk of the information inside of it that we are going to want to take a look at. So what I'll do is I'm going to run binwalk with a -lowercase e to extract the firmware, and we'll give it the name of the firmware and hit enter. I'll clear the screen and do an ls. Now we have a new directory that has been created called _mercury.bin.extracted. And we will cd inside of that directory. And now if we do an ls, we have quite a bit of information. This is everything that it was able to extract, and it should immediately become familiar to you that this is running on Linux. This is basically a scaled down version of a typical Linux operating system. Before I begin a basic data review of what we have here in the file system, I am actually going to scan for viruses, rootkits, and any potential backdoors. You're going to run the command sudo apt install clamav and clamav-daemon, and I'll do a -y to accept, and we'll hit enter. I have both of these installed already. The next thing that you're going to want to do is stop the daemon from running. So we'll run the command sudo systemctl stop clam av-freshclam. Now if I run the command sudo systemctl status clam av-freshclam, we should get back that it is inactive, and we do. The reason why we're stopping it is because we need to update our database that stores all of these signatures for viruses and so forth. Next thing that I will do is run the command sudo freshclam. That updates the database that contains all of our signatures. Now I can restart the daemon by running the command sudo systemctl start clamav freshclam or freshclam.service, either or. And if I do a systemctl status on that daemon, we should get back that it is active and running, and we do. And now we can scan our newly acquired file system to see if we have any viruses. So I'm going to back up from outside of the directory that contains the file system and go back to the parent directory where we're doing everything from, which is the mercam firm directory. And I'm going to run clam scan. I'm going to do a -- log, and I'm going to save everything to a log file. So I'll do an equal sign, and then I'm going to call the file clam.txt. Next thing that I'm going to do is going to be a -r, and I'm going to give it the name of the directory that I want it to start the scan from. And that directory is going to be the _mercury.bin.extracted directory. And I will hit enter. Okay, so it has finished the scan. At the bottom we get a scan summary, it is using a database with what appears to be almost 9 million known virus signatures. It scanned 97 directories, it scanned 450 files, and it found 0 infected files. So that's good for us. So if I do a what is on check rootkit, we get back that it is used to scan the system for signs of rootkits. If you want to install it on a Debian-based system, just run the command sudo apt install check rootkit. I can pull up the help menu by running check rootkit -- help. Very limited set of options. We're going to do -l, lowercase l, to show the available tests that this performs. And then after that, the only option that we're going to be using is the -lowercase r to specify the directory that we want to use as the root directory. So I'll go ahead and run check rootkit with a -l, and this shows you all the tests that it does. And now we will run the command sudo check rootkit -lowercase r, and we're going to give it the name of our parent directory, which is going to be the directory that we extracted the firmware into, and hit enter. On the left hand side, it's showing us that it's checking for certain things. Then on the right hand side, it's basically telling us either that it was not found, or that it was not infected, or not tested. It also says no suspect files, which is a good thing, and I don't see anything in this output that is alarming to me, so I can move on to the next thing. Okay, so now we are going to do basic data review of the file system. There are numerous commands that I can use to do this. This is basically dependent on how you like to do things and what commands suit what it is that you're doing and you're trying to see. So ls is the go-to command for so many of us, and you could just do ls-l with a capital R. The -l will do the long format, identify permissions, the date, etc. The -R will list recursively through directories. Get quite a bit of information. We could also redirect this to a file and save this. If I were to do that, it would be something like this, ls-lr, and I would redirect it to a file that I would probably call ls-r.txt. And we can do a word count on that, and we see that it is a little over 1,000 lines long. I'll run the find command, and I'm going to run it on the directory that is where we extracted the firmware, and I'll do a -type, and for the type we are going to do F for file. And what we get is a list of files, 1 per line. Once again, I can save that to a file. And if you're wondering why I'm not just going up in my command history, it is because the way my system is configured, I do not save commands. There is no command history. So that is why you see me retyping the command pretty much every time. So I'll run the command once more. I'll do find on the directory, -type F, and I will redirect that to a file that I will call file.txt. We can also get a list of directories, 1 per line, and now I'll do that by running the command find. Once again, on the directory where our firmware is stored, I'll do a -type, and instead of F for file, we'll do D for directory, and I'll go ahead and redirect the output of this to something that we will call file-d.txt. And if I cat out the contents of that, so we have one file that is showing us a list of files, 1 per line, and another one showing us a list of directories, 1 per line. You can also use the tree command. If I do a what is on tree, get back that it is used to list contents of directories in a tree-like format. This is probably the easiest of the tools for data review, and it also is the most visually pleasing. That's why I like using it. So very simple. I'll just cd inside of the directory and I'll run the tree command. It's colorized. It has organization to it. It's a very good command, very simple. And if you go back down to the bottom, one of the things I really like about it is it gives us a little summary and tells us that there are 105 directories and 680 files. I'll cd back into the parent directory for our purposes. Once again, I could save this to a file, run the tree command, redirect the output to a file that, you guessed it, I'll call tree.txt. You're starting to understand the methodology at this point. Next thing that I'll do is make a list of file types. The file command compares each file's header, which is the first few bytes of a raw file or whatever defines that file, with the contents of the magic file. It then outputs a description of the file. So what we're going to do is we're going to use the file command within the find command. So we're going to have the find command run the file command on each line. So I run the command find. We're running this on the directory where we've extracted the firmware to. I'll do a dash type, and for the type we're going to do F for file. Then we're going to do a dash exec, which is basically saying that the find command is going to execute a command on each line of output, and the command we're going to execute is going to be the file command. We do curly braces as a sort of placeholder, a backward slash, and then a semicolon. And let me go ahead and just copy this now because I'm going to rerun this here in a second. Okay, so I hit enter, and that is what it looks like. So we have a list of file types. A lot of these show up as just ASCII text. Then we have executables. We have binaries, stripped, not stripped, etc. and so forth. And you guessed it, we want to save the output to a file. So I'll rerun that command, and I will redirect that to a file that I will call file types.txt. Another thing that I might be looking at is the permissions on each of the files, specifically looking for set user ID permissions or permissions that have the executable bit enabled. So I can do find on our directory where the firmware is extracted to, and we'll do a dash perm for permission, and we're going to do a dash u equals s, and then we're going to do a dash type. The type is going to be file, and then we're going to do the nice little thing here that we do at the end where we do a to, and we redirect everything to dev null, which basically takes all of the errors. Instead of printing them to the screen, it throws them somewhere on our system where we don't see everything, and it makes it look all nice for us on the screen. So I will hit enter, and we actually have nothing, so it didn't find anything. So I'll move on to the next one, and I'll look for any files that have the executable bit enabled. So I'll do find on that same directory. We're going to do a dash type, and we're going to do F for file, and we're going to do a dash executable. Once again, we are going to throw everything to dev null and hit enter. And this time we do get some results. So here is a list of all of the files that have the executable bit enabled on it. And those might be of interest for us to look at because that means that those are going to be running with a higher set of privileges enabled. And I will go ahead and rerun that command and save the output to a file. I will call that file executable.txt. And we'll cat out the contents to make sure that it is there, and it is. So I'm over here at the GitHub page for what is called PEAS. PEAS is an acronym. It stands for Privilege Escalation Awesome Scripts Suite with colors. And if we scroll down the page, we are brought to a section where we learn that there is a set of scripts that can be used for Windows privilege escalation, and then there is a set for Linux privilege escalation. So we are going to click on the link for LinPEAS. That takes us to this page. Now we can scroll down the page and we are brought to a section called Quick Start. That is going to give us different options to acquire the script as well as executing the script. For example, you might have to deal with bypassing antivirus. We don't have to deal with any of that in our situation. There is a section called Firmware Analysis. That's the section that we are interested in. If you have a firmware image and you want to analyze it, you can use LinPEAS to search through that image for passwords and or bad configured permissions. We have two main options. One, we can emulate the firmware and then run LinPEAS inside of it. Or if we cannot emulate the firmware, then we can just use the -F option and provide it with the path to the folder that the firmware image is residing in. We are going to be using the second of the two options because we are not emulating the firmware, though that may be something that we might consider doing in the future in a separate video. So the first thing that I'm going to have to do is acquire the linpeas.sh script. I'm going to come over here to the releases page. So I will click on the releases page, and we have many options to choose from. But I'm going to be going with the very first option. This is the linpeas.sh script. I will copy that link, go to the command line, and inside of what is our parent directory for everything that we are doing, mercamfirm, I will use wget to get that script. Now if I run ls, you see that we have a file called linpeas.sh. If I try to execute this script, I will not be able to do so. And that is because I do not have the proper permissions in place. So we have to change the execute permission bit on the script, and we do that by running the command chmod +x and give it the name of the script. Now if I do an ls, you will see that linpeas.sh shows up in green. That's another indication that this bash script has the execute permission bit enabled. Now that we have the script and we have the proper permissions in place, we simply need to run the script. Okay, so to run this script, I can do this a couple different ways. I could do a // and then give it the name of the script, or I could run the command bash and then give it the name of the script. And this is the way that I'm going to do it. We want to pull up the help menu, so I'll do a --help. We're going to be doing a -A to perform all checks. We're also going to be doing the -F option underneath firmware recon, and that's going to be used to execute linpeas inside of a particular folder. So I'll run the command bash on linpeas.sh. We will do a -A and a -F, and we will specify that directory and hit enter. Okay, now that the script has completed, let's go back up to the top and see what we have from the results. First thing that we are given is a legend. That legend is using colors. So we want to be paying attention to anything that is in red or red and yellow. Some of this initial stuff under basic information actually pertains to the system on which I am running the script and not on the firmware image. But when we come to the section titled Interesting Writable Files, owned by me or writable by everyone, that is where we begin to see information that is usable that pertains to the firmware image. And remember, we're looking for red or red and yellow. So we do get some hits back on the lib directory as well as the sbin directory. We can see that we have some hits that come back that are in red and yellow, which according to the legend had the highest % chance of this being an area to pay attention to that could have misconfigurations. We do also get some hits back underneath the section titled Interesting Group Writable Files. And the script has even been so kind as to give us the file date times. Underneath the section titled Executable Files, potentially added by the user, we have several hits that come back, and that is pretty much all we are going to get from running the script. So as we have seen, the LinPEAS.sh script is not only a valuable tool that can be used for privilege escalation, it can also be used for firmware images. All right, now let's just take a manual approach and let's look inside some of the files inside of this directory. So if you're familiar with Linux, then you're going to know that the password file is going to be of interest to you. So let's go ahead and see what's inside of that. And what we see is we have all of the users on the system, as well as if they have a shell or not. Most of these users, they do not have a shell. It says false on the back end. But we do have one that does actually have a shell, and it is the root user. So that is definitely of interest to me. We have not just a root user on this system, but a root user that does have an accessible shell. Naturally, the next thing we might take a look at after the password file is going to be the shadow file. So if we cat out the contents of that, once again, same structure, the users on the left, and then the asterisk is denoting that we have. The asterisk denotes that a password has not been created for the account, but from this point, I think it's time to go into what I would consider to be the most important part of this file system, and that is the squashfs root file system. There are two directories over here on the right. Both of them appear in blue, designating that it is a directory. So let's go ahead and do the first one first, and then we'll do the one underneath it with the -0 on the end. We will cd into squashfs-root and do an ls. And this is basically a Linux file system. This is your root directory of a standard Linux file system. In fact, if I do an ls of my root file system on this system, you can compare the two and see that they are incredibly similar. So we have all of our binaries in the bin directory. Let's go ahead and take a look at the etc directory. Let's cat out the contents of the shells. So we only have two shells on here. We have the sh shell and the ash shell. We have the group. Here are all of our groups on the system. If we cat out host name, we'll get the host name of the camera, and this host name is whale. All right, let's go ahead and go back into our parent directory for this, and we're going to go into the other squashfs directory. Let's take a look at what we have in here. So it seems like it's a little bit more streamed down than the previous squashfs directory. I'm just going to do a tree command inside of this and see what we get. So we have 16 directories and 115 files. I see some sounds in here. So this is obviously containing some of the sounds related to sounds that the camera makes. We also have images and some things pertaining to the time zones and some more libraries. Okay, so we are still poking around in this second of the two squash fs root directories, and a couple things that are worth pointing out. So inside of the lib directory we have various libraries, but I also see that we have the file over here on the right for OS release. So if I cat out the contents of that, that lets us know that this is using a build root and the version of 2018.08.1. I see that we have a Python script over here ending in .py and clearly is something related to GDB for debugging purposes. So I want to take a look inside of this stream directory real quick. Now, if we see the inside of that, we have a .sh file that implies that perhaps this is a bash script. If I use my nanotext editor to open this up, sure enough, it is a bash script. Now, I understand bash, but I don't write bash very much. So what do? I want to understand what this script is doing. Maybe I think it's doing something it's not supposed to be doing, and we are reverse engineering, right? So we are trying to understand what's running on this, what's going on this, and that includes scripts such as this one. So a great thing that you can do is you can simply just copy this script and you can use ChatGPT. So I've already done that. I'll bring that window over so that you can see it. Didn't even log in. I just went to ChatGPT and I pasted the script into the search box. This is what it looks like after I pasted the script inside of it, and it says that it looks like we have a shell script designed for managing a streaming process, handling temporary files, and checking for the presence of an SD card. And then it gives me a breakdown of what the script does. So this is great. This really will help you understand what's going on with certain scripts and further the reverse engineering, which is our main goal in this. If I go back to the file system, we also had a directory that has images inside of it. So let's see the inside of that. Now, if I run the file command with an asterisk, it will just run the file command on every one of these files, and we can see that they are all bitmaps. So I can use the display command to open these up, and if I do a what is on that, it tells me that this is a command line utility to create, edit, compare, convert, or to display images. We are using it to display images, so I'll pick one. I see there's one here called pepper, so if I run the display command on that, this is what the image looks like. So we can actually take a look at the images that are on this camera. And we'll take a look at one more. So I see we also have a image for Genie on here. So let's go ahead and see what that looks like. And this basically is related to the camera. It's a Mercury smart camera, and that's what that looks like. So pretty cool. That's how you do that. All right, so I want to take a look at something else here. So I'm going to go back into that first squashfs root directory. And inside of the Etsy directory, we have our configuration files, but we also have this initd directory, and this is pretty important. So let's cd inside of that. We have nothing but bash scripts. I can do the file command on all of these, and every one of these is a bash script. I can also run the word count utility on this. If I do an asterisk, it'll run the word count on every one of these, and we can get a quick look at which ones are bigger than the others. So we see, for example, that we have a bash script called s60anka.sh. I remember seeing this on the chip on the CPU. I'm going to take a guess and say that this has something to do with functions performed on the CPU, and it is the biggest of all of these bash scripts. So this is 206 lines long. But these are all going to be important because these are bash scripts that are typically going to be executed upon starting up the camera. So let's go ahead and take a look at this particular bash script. And this is what it looks like. Now, once again, let's take the approach of you don't know how to read or write bash. We want to know what is going on. So let's see if we can get ChatGPT to give us some more information about this. This is a much longer bash script than the others. Let's see what happens. So I'll go ahead and cat out the contents of that script. And let me go ahead and copy everything. Pull my web browser back over to the screen, and let's go ahead, erase that, and paste this bash script into the search box. Let's see what we get. And it does work. That's great. So it tells us that the script seems to be a startup script for the device, likely running Linux. That initializes various hardware components and drivers, particularly for sensors and network interfaces, and it gives us a brief breakdown of its structure and functionality. Very nice, very good, very good. We have learned a lot about the firmware image that we extracted from this camera. Perhaps in a future video, we will begin the process of reverse engineering specific binaries that reside inside of the firmware image. And we will use tools like objdump, readelf, xxd, as well as the Radare framework. But that's going to be it for this video. So from this point, it is now on you guys. You have the firmware image, you have a basic understanding of reverse engineering, so have at it. Do some reverse engineering on your own and share the results. Let us know what you find. Let us know what ways you were able to do things. What tools did you use? As always, thank you guys for watching. If you haven't done so already, please subscribe to the channel, like the video, and post a positive comment. And as always,
stay fresh.
We'll see you in the next one.